Okay, one last thing we're going to talk about is the speed of a lens system. In other words, how much light is collected from a point source. This has two different names. Um, the F number is used for everything but microscopes. And remember, the F number is defined as F over D, which is the focal length divided by the diameter. Now, that works great if you have just a single lens and a camera sensor, because the distance from the lens to the camera sensor is your focal length, and the diameter is your diameter of your of the cone of light that's hitting the camera sensor. But um, in reality, that rarely ever works well. So you can also take the, if this is the half angle, right? We know that our F number is also equal to 1 over 2n sine theta, where n is the index of refraction of the material in front of the camera, and sine theta, theta is the half angle of the light cone hitting the camera sensor. Um, it's also worth noting that for microscopes, so F over D is also equal to 1 over 2 sine theta, which is equal to the F number, which is equal to 1 over 2 times the numerical aperture. So if you want to calculate the numerical aperture, you just invert all of this stuff and you get, oh, forgot to add an n here. There's an index of refraction there. Calculate the index of refraction is just 2 times the inverse of the F number. So as the diameter increases, we gather more light and the F number decreases. Yeah, decreases. So um, when you have a imaging sensor, and there's reasons to decrease the diameter in terms of decreasing aberrations, but the cost that you pay is you raise your F number, which lowers the amount of light you collect, which makes your lens slower. As we also saw earlier, it also changes the depth of field, right? So, and it also, although we haven't talked about this yet, we will later, it changes the resolution, the diffraction limited resolution, which isn't so much an issue with like camera systems, but it becomes a real issue with microscopes or telescopes. Great. So F number works for simple systems. F equals 1 over 2 sine theta for more complicated systems. How do we find theta? We find the exit pupil and then calculate the angle. All right. So here's our new optical system. We have an image or an object 11.63 millimeters off of the optical axis, located 168 millimeters from the first lens, which has a 50 millimeter focal length. We have a second lens, which has a negative 75 millimeter focal length, and then a third lens, which has a 75 millimeter focal length. By the way, symmetric lens systems like this, where you have a positive, negative, positive, or negative, positive, negative, or as we'll talk about, we can put meniscus lenses in there too. But adding symmetry like this is a way of reducing aberration. So it's pretty common to see. But we've put in a aperture stop right here. This is our aperture stop. And it has a diameter of 12.5 millimeters, which is half the diameter of these lenses. So clearly this is going to be limiting our cone of light, especially given the spacing of these, which is 10 millimeters and 10 millimeters between both the lenses. So there's not a lot of room for the light to change its diameter until it hits this aperture stop. Great. So we know that that's our aperture stop. So we've done that. Now let's image that from the object's point of view. So sorry, we have to image it from the camera's point of view. Man, I got that wrong. Sorry about that. So our SO in this case is going to be 6.5 millimeters. So our HI from the right-hand side is going to be 6.5 millimeters. So our HI is equal to 6.5 millimeters. Our distance is 5 millimeters, so SO is equal to 5 millimeters. And our focal length for our second lens is 75 millimeters. Focal length for our second lens is 75 millimeters. So if we solve for SI, SI is equal to, now you'll notice that our SO is well within the focal length of our lens. So even though it's a positive lens, it's not a strong enough positive lens to converge all the light, the rays leaving our object to another point source, to another point. So it's going to be, the rays are still going to be diverging after the lens, just less so. So what the result of that is that we have we're going to expect to have an imaginary image. All right, so our image occurs at negative 5.35 millimeters. So it's negative, which indeed is an imaginary image because it's on the same side of our lens as the object. Now, if we calculate our magnification is just going to be equal to negative 5.35 divided by 5. And so that is just 1.07. So our magnification is equal to 1.07. And that tells us that our HO was 6.5 millimeters. Our HI is going to be equal to 6.5 millimeters times 1.07 gives us basically 7 millimeters if we round it. Great. So now we know that our height is 7 millimeters and our location is 5.35 millimeters from our last lens. So if we wanted to figure out what our F number is, our F number is equal to F over D, or it's equal to 1 over 2 times n sine theta. So we can calculate what theta is and then calculate this, or we can calculate F over D. So let's do both. So F over D in this case, our rays appear to be coming from so our plane is, our plane of our aperture is right after our actual aperture. Sorry, plane of our exit pupil is right after our actual aperture. And then it's slightly larger, not much, just slightly. So here is where our exit pupil is. That's our exit pupil. And we can do this two ways. One, we can draw a cone of light that leaves our exit pupil and ends at our camera. This is our F, and this is our D. So in that case, our F over D, F is going to be equal to 5.35 plus 50. So 55.35 divided by our diameter, and our diameter in this case is 7 times 2, so it's 14 millimeters. So 55.35 divided by 14 millimeters is equal to 3.95. So 3.95 is our F number, which is actually fairly fast for an imaging system. That's pretty good. We can also calculate it using 2n over sine theta. In that case, we know the location of our exit pupil here, and we know these distances, so we can actually calculate this theta here. And you're going to notice that they're going to be different from each other because 1 over 2 n sine theta is the accurate way of doing this, and f over d works for small angles. So our theta is going to be equal to the tangent inverse of 7 millimeters divided by 55.35, which gives us 7.2 degrees equals 7.2 degrees. Great, so now we plug that into our formula. We have air in between our lens and our camera, so our F number is just going to be equal to 1 over 2.0 times 1.0, which is the index refraction of air. Actually, we usually use n air, times sine of 7.21 degrees. So we take 1 divided by 2 divided by sine of 7.2 degrees gives us 3.98. So even for an F number of 3.98, 3.95, the F over D works as a pretty good approximation. Where it breaks down is when you start getting higher and higher, lower and lower F numbers. If you get an F number near 1, this is going to break down even more. But apparently above 4, or probably even above 3, this works fairly well. Great. So that's the F number. Like I said, a pretty good lens has an F number of 1.2 or so. Middle, that's a fast lens. Medium strength lenses are 6.0, and slow lenses are on the upside of like 12 to 20. So, all right, that's it. And then next we're gonna start talking about aberrations, what they look like, and then how we can correct them.